If A1 divides A2, then we can write A2 as a product of A1 and some other number. If A2 divides A3, then we can write that A3 is a multiple of A2. And substituting for A2, we have that A3 is A1 multiplied by 2 of these factors. So our sequence looks like this. We have our first number A. Our second number is A times some ratio. Since this divides our third number is A R2 times our next ratio, and so on. Since all of these numbers are integers, and our sequence is strictly increasing, our common ratios are also going to be integers, and they're all going to be greater than or equal to 2. We are interested in the sum of all these terms in our sequence. Let's factor A from all of these terms, and we notice that we can factor R2 from all but the first term in the parentheses, and so on. We can factor out R3 inside of these parentheses. We want this sum to be equal to 360, and since we're going to be doing a lot of factoring, let's find the prime factorization of 360. Factoring is going to depend on the length of our sequence, so let's do casework on n, the number of terms in our sum. We'll start with n equals 1. That's just our first term is equal to 360, which gives us our first sequence. This is our expression for n equals 2. We'll set it equal to 360. We again note that since we have a sequence of integers and they're strictly increasing, all of our common ratios are going to be greater than or equal to 2. So the second factor is greater than or equal to 3. This means our second factor cannot be equal to 1 or 2. Counting the number of factors that divide into 360, we have a total of 24 factors, of which 2 of them are invalid. So this gives us 22 more sequences for n equals 2. Let's see what happens when we have 3 terms in our sum. This expression, when fully factored, looks like this, and we set it equal to 360. Again, R2 and R3 are both greater than or equal to 2, which means the second factor is greater than or equal to 7. Let's make a list of all of our factors of 360 so we can eliminate the ones that are less than 7. This means our second factor is not 1 through 6. This leaves 18 possible factors for A. So we'll check all the values of A less than 60 that divide into 360. Let's do this in a table. Let's start with A equals 1. That means our second factor is 360. Subtracting 1, we get 359 as the product of 2 numbers, both of which are greater than or equal to 2. Since 359 is prime, we don't have any sequences here. Let's try A equals 2. Our second factor is 180. Subtracting 1, we get 179, which is also prime. So we can't pull out an R2 that's greater than or equal to 2. Let's try A equals 3. This gives us 119, which is actually not prime. It is 7 times 17. So R2 can be either 7 or 17. If R2 is 7, then 1 plus R3 is 17, making R3 16. Likewise, if R2 is 17, R3 is 6. Out of curiosity, let's pause for a moment and see what this sequence looks like. When A equals 3, R2 equals 7, and R3 equals 16. We have 3 times 1 plus 7 times 1 plus 16. And distributing carefully, we have 3 divides 21. 21 divides 336. And we get the correct sum. Let's continue. When A is equal to 4, our next factor is 90, giving us 89 over here, which is prime. 5, 72, 71 is prime. 6, 60, 59 is prime. 8, 45, and 44. The prime factorization of 44 is 2 squared times 11. Our r's have to be greater than or equal to 1, so we'll pick 2 and 4 and 11 for R2. Subtracting 1 from the other factor gives us 21, 10, and 3, giving us 3 more sequences for A equals 8. When A is 9, we get 39, 3 and 12, or 13 and 2. When A is 10, this is 36, this is 35, which is 5 times 7, giving us 2 more sequences. When A is 12, there are no sequences. Nothing when A is 15. When A is 24, we get 14 over here. That's 2 times 7. When R2 is 2, R3 is 6. We can't have R2 be equal to 7 because that would let R3 be equal to 1, and our Ri's need to be greater than or equal to 2. Our next factor is 30. Here we get 9, that's 3 times 3. 3 and 2, 40 times 9. This gives us 8. We can have R2 is 2 and R3 is 3. Any other factor is going to be invalid. Finally, we get to A is equal to 45, and this is prime. So for n equals 3, we get 12 more valid sequences. Let's see what happens when n is equal to 4. Our expression, when fully factored, looks like this. Let's compare it to our expression for n equals 3. In our previous sequence, we replace our previous value of R3 with this new product, the new R3, times another number. Our other variables, if they were valid for n equals 3, then they're also going to be valid for n equals 4. Since we're replacing an old R3 with a number that is a product of two numbers greater than or equal to 2, this expression on the right is not prime. So we can look at our old list of solutions for n equals 3 for values of R3 that are not prime and just test those. Also again, since R3 and R4 are integers greater than or equal to 2, this expression is going to be greater than or equal to 6. So we're looking for R3s from our old list that are not prime and also greater than or equal to 6. Looking at our old list, we find these values. I'll copy them over here. Here are our values. Let's see if we can replace our old R3s with this new expression as the product of two numbers. When this expression is equal to 16, R3 can be either 2 or 4. R4 is going to be either 7 or 3. For 6, we'll have R3 is equal to 2 and R4 is equal to 2. For 21, we can have 3 and 6 or 7 and 2. 10 gives us 2 and 4. 12 gives us 2 and 5, 3 and 3, and 4 and 2. 6 gives us 2 and 2. We have that for two different values of A. As an aside, let's check this last example and see what the sequence is. We'll plug in our values for A and our R's and distribute carefully so that we can see the terms of our sequence. Here's our sequence. Each term divides the term that comes after it, and the sum is equal to 360. So for 4 terms, we get 11 additional sequences. Now we'll look at n equals 5. Here's our expression. Let's compare it to the one for n equals 4. And again, we're going to replace our old R4 with the product of two numbers that are greater than or equal to 2, which means we can use R4 from n equals 4 such that R4 is not prime and R4 is greater than or equal to 6. We have one value that satisfies these requirements. This came from A equals 8, R2 equals 2, R3 equals 3, and R4 equals 6. We're going to replace this R4 with a new R4 times 1 plus R5. This gives us a new R4 of 2, and R5 is also equal to 2. This gives us one more valid sequence. We can't do any more replacements because our R5 is prime, so we can total up our sequences for all of these cases. For n equals 1, we just had one sequence. N equals 2 gave us 22 sequences. Here's n equals 3, n equals 4, and one more for n equals 5. This gives us a sum of 47, and that's our answer.